Start. Okay, I'm Hiro Takami, and I'm gonna chair for the next three speakers. And the first one is Speaker Baobab, and he will give a talk about the dry path or possible dry path for planet formation. And each talk should be 15 minutes plus 5 minutes for questions. Okay, so please start.
Thanks very much. So, good morning, everyone. So my name is Hao-Yu. Usually people call me by my nickname, Baobab. So I'm from Taiwan, so from San Yat-sen University. So it's the southern part of the country. So this picture is a scene from my university. So this beach is just 3 minutes walking from my office. So if you are interested in some of my profiles, you can use this QR code. So it direct to my personal webpage. So I'd like to thank the organization committee. So it's a really great event for me to come and meet everybody. So it's including some of the collaborators and some new faces. So today I'd like to present a hypothesis about the dry path of planet formation. And just to frame the problem, so I'd like to first introduce what I refer to the wet path of planet formation. And it's actually what everybody has been relatively familiar about. So it is a planet formation in a relatively large polar planetary disk. So in most of the area of this polar planetary disk, the temperature is low. So then you can convince yourself that the water ice is coated on the surface of the dust grains. And it has been believed that the water ice coating is what makes the dust particles sticky enough to coagulate with each other to form the big particle, the chondrule, the millimeter-sized particle, and the pebbles, the centimeter-sized particle. And when your dust particle in the planetary disk grow to that kind of size, so they start to become dynamically decoupled from the gaseous disk. So they start to migrate inward until they touch the water snowline. So where your volatile start to be evaporated, so locally develop the pressure maximum. So that pressure maximum help you to trap all of the inward migrating icy pebble at that radius. So then you form all of the planetesimal at that radius, and you form the planet at that radius. So this is a relatively well-accepted model. One of the issue I can think about for this model is that so this water snowline usually have 1 AU or sub-AU radius. And you know that so for the disks that are quiescent, so this scenario of forming a planet may be okay, but now we are working in the community of looking at the accretion burst, then you know that whenever the planetary disk is having the accretion outburst, then the high temperature region expand, right? So then so you use some time to accumulate the pebble size. You accumulate the icy pebble at the water snowline, but probably every 10 to the 3 to 10 to the 4 years, you hit the icy pebble with the outburst, so you probably destroy them, all of them, right? So then you start all over again in the process of forming planet. So this seems to be the problem, but so if you have a way to create the pressure maximum at the outer radius, then it may be okay, right? So for example, so if you have a planet in the disk, then the planet-disk interaction probably help you to create the pressure maximum at the outer radius. So for example, in the PTS-70 disk, so the planet-disk interaction help you to create the pressure maximum, so it help to form a large dust rain. And the planet-disk interaction probably create a vortex in the northeast of the PTS-70 disk, which can be seen in the ALMA band 4 image. And outside there's a poster presented by Daniel, so which is using the observation of Simon. So they achieve a better angular resolution. And with the SED analysis, so we can see that in the vortex. So the ALMA and VOA SED fitting, so it tells you that the maximum grain size in that vortex is probably achieving 1 millimeter size. So it allows you to form planet if you can trigger the streaming instability in that vortex. And there's another similar case, so DM tau. So there's a inner ring, so which look like a azimuthally symmetric ring in the ALMA image. But if you go to the JVOA band, so with lower optical depth, you see a lot of clumps in the inner ring. So it looks very azimuthally asymmetric. And if you try to do the SED analysis, you find that the maximum grain size in those localized clumps seen in the VOA image reach several millimeter size. So this could be one way of forming planet, right? So this could be one of the wet paths of forming planet. So it help you to understand the formation of ice giant or the formation of comets. And there's probably another way of forming planet in the icy world in the protoplanetary disk. So there are many colleagues, including Edward, so they mentioned that the gravitational instability, so when it is triggered, so it may induce fragmentation in the disk, so it can form ice giant in that way. And there are some scatter light image, so around the FU Orionis object that may be related to the large spiral structure created during the gravitationally unstable phase. So now we at least have two mechanisms to form planets in the icy world. So what could be the problem, right? So that helped to understand the formation of gas giant and ice giant as well as comet. But if we come to the formation of the Earth, then if you look at the composition of the Earth, you realize that to form the Earth, so which is dominated by silicate, right? So we don't have a lot of water, we don't have a lot of carbon. So before forming the Earth, you need to remove 99.9% of the water from the ingredient of forming planet. You also need to remove 99.9% of the carbon from the ingredient, right? So you need to heat the ingredient to very high temperature. And if we already form planet that has a lot of water and has a lot of carbon, it's relatively difficult to do that, right? So like on the Earth, so we have a glass of water. If you heat the glass of water to 300 Kelvin, you don't remove those water to the space, right? It's because they are trapped by gravitational potential. So the more easy way to remove those ingredients is that you remove them, so you heat the interstellar dust when the dust particles are still small. So with this idea, so now I start to think about, so in order to form the Earth, so we probably need to allow the dust particle, so in the high temperature region, so in the inside of the water snowline, so where the dust particle is free of water ice and probably free of the carbonaceous material to coagulate to large size and to form planetesimal and planet in situ. So we need to form those large dust particles and planetesimal within the water snowline. And that required the dust particle, especially the bare silicate grain, to be very sticky, right? So to be sticky enough to coagulate to large size, at least to millimeter size, in order to further trigger the streaming instability. So to test this idea, then what can we do, right? So then we try to measure what is the dust grain size inside of the water snowline, right? So if we cannot detect the large dust grain inside of the water snowline at all, then this idea is immediately falsified, right? So it means the dust particles are not sticky after you remove the water ice. So then, so to measure the dust grain size inside of water snowline, so for typical T-torrid, this is actually very difficult, right? So we know the snow line is very small. So if you try to carry out AMA and JVOA observation and to do the SED analysis to constrain the maximum grain size, it's just impossible, right? So you don't get enough angular resolution and you don't get enough sensitivity to do that. And the accretion outburst help us to do this kind of experiment because it makes the water snowline expand in terms of size by at least 1 order of magnitude. Right? So in terms of radius, increase by 1 order of magnitude. In terms of area, increase by 2 order of magnitude. So then, since 2019, so I tried to do this kind of experiment by looking at the archetypal FU Orionis object, so just FU Ori. So I tried to, based on the SED analysis, so the data is taken from ARMA and JVA and try to constrain based on SED fitting the maximum grain size inside of the water snowline in FU Ori. And so some of you may know that, so when we do the SED analysis using this kind of data, we may be confused by the effect of dust scattering. So have I considered that? So I actually did. So it's actually one of the phenomena that identified by me. Okay, so let me show you. So what is the data I've been using? So in the infrared band, so we have the VLTI gravity spectrum, and also we are using the Spitzer and Herschel spectrum in the mid and far infrared band. And with ARMA, so we are taking the bands 7, 6, 4, and 3 data. So they have very small error bars, so it looks very small in this plot. And also we have a lot of JVOA observation, which is particularly useful when you try to constrain the millimeter size grain. And yeah, so then we do the SED fitting. Here I just straightly come to the schematic schematic picture of my SED fitting result. So in the FU Ori disk, so this schematic picture shows you the upper half of the FU Ori disk. So we have a relatively outer part of the disk outside of 10 AU region. The temperature is relatively low, it's 50 Kelvin-ish. And in the inner 10 AU region, it's very interesting. So there are several evidence that this region is dominated by viscous heating. So first, the surface of the disk is having lower temperature than the midplane of the disk. So we can measure this because we have multiple wavelengths observation. So with the long wavelength observation, which is optically thinner, we trace the disk midplane. With a short wavelength observation, we look at the surface. So we can get the vertical temperature distribution, and this vertically inverted temperature distribution can only be created when the region is dominated by viscous heating. And yeah. So if you look at the radial temperature profile, then it's very interesting. So if you look at the temperature distribution at the disk surface, it is also actually consistent with the R to the minus 3/4 temperature profile. That is telling you that this region might be dominated by viscous heating. It's actually out to the 10 AU radius. And if you extrapolate this temperature profile to the inner region, it's actually a good comparison with the VOTI observation presented by Aaron 2 days ago. And this temperature profile tells you that the FU Ori disk is probably having the accretion rate between 10 to the minus 4 to 10 to the minus 6 solar mass per year. And in this region, so it's very interesting. So we have the constraint of maximum grain size from SED fitting. So in the 50K region, so which is outside of water snowline, we get an upper limit. So the maximum grain size is 200 micron. So in this upper half of the inner disk, inner 10 AU disk, so which is still outside of the water snow line. So water snow line now is a 2D contour. So in this region, we also get the upper limit of the maximum grain size is 200 microns. It tells you that outside of the water snow line, the dust grain doesn't grow too much. But inside of the water snow line, so in this midplane, which is having the temperature of 370 Kelvin, we only get the lower limit of the maximum grain size. It's 1.6 millimeter. So this is very counterintuitive. So we actually try to repeat the experiment. So there's 2 publications, so one in 2019 and one in 2021. So they are very consistent with each other. It tells you that it's possible for dust grain to grow to millimeter size even inside of the water snow line, so which is opposite to what people used to believe. And in this region, so there are more physical parameters we can constrain. So in the viscous dominant disk, so basically the surface temperature tell you what is the accretion rate in the disk at that specific radius. And the vertical temperature profile give you one constraint on the disk surface density, right? So that is the vertical radiative heat transportation. And also your SED fitting get you another constraint on the disk dust and gas mass surface density. So if you know the accretion rate from the surface temperature, and if you know the surface gas density, you can actually derive what is the viscosity, right? So in the viscous dominant heat, viscous heating dominant disk, that's what you can do. And if you try to do that, so assume you have a standard Sunyaev alpha disk, you get the alpha parameter consistent with 1.0 in the inner 10 AU region. So it's a maximally MRI active disk. So in that case, you can try to estimate, so what is the turbulent velocity in the disk? And with that, you can further try to estimate, so what is the expected average collisional velocity between your dust particles? So with the constraint of the dust maximum grain size, you can try to tell, so what is the collisional velocity that your large dust particle is surviving? So I give a very fundamental constraint on the physical parameter that is related to the stickiness of dust particle. So then we came up with a number. So there's a parameter called fragmentation velocity. So we say the inside of the water snow line, the fragmentation velocity of the dust particle is maybe above 10 to 20 meters per second. It's actually mean the dust particle without water ice coating is very sticky. So previously, people think this number is 1 to 2 meters per second, right? So now we get a number which is 1 order of magnitude larger, at least. So when I first presented this result in Tokyo, so everybody thought I was crazy, except one person, so Satoshi Okuzumi. So he told me that so the laboratory experiment people start to tell the same thing. So they start to say, so removing the water ice is actually making the dust more sticky. So it's probably the key for the terrestrial planet formation. And also, so there are observation that is presented by Yamamoto-san. So in a poster, and also the next speaker, so they are going to introduce the measurement of other systems that may be consistent with the idea that the large water ice-free dust particle, they can survive the high temperature environment. So as long as you can trigger the streaming instability in those high temperature environments, there might be a chance to form the Earth-like planet in situ. So I'll stop here. Thank you very much.
Thank you, Baobab. So any questions? Okay, go ahead, Lee.
So my recollection was that the VLTI active region was like 0.3 AU, and you're going out to 10. So obviously there's different sensitivity at different wavelengths. Could you comment?
Yes, so I believe that the VLTI, so if you look at the infrared emission, it probably only allow you to trace out to 1 AU-ish region. Right? So in that region, so you're looking at the non-Rayleigh Jeans limit. So if the temperature become lower a little bit, then the flux density become very low. Now our measurement is entirely made in the Rayleigh Jeans limit, right? So as long as you integrate long, so I give you more chance to look into the more extended region.
Okay, Peter?
Yeah, thanks. First, I think the comment that this VRTI is this gravity, what used here. So if we add Matisse, and there are Matisse observations, we published a paper with Pietro Matisse, then it can sample a little bit larger radius with the VRTI. The other would be just a question. Well, this is the wavelength range very well observable with the James Webb MIRI. Would you have some predictions for the MIRI spectrum? What should we see?
So because this source is so well observed by Spitzer and Herschel already, so I'm not sure if there's anything super new, but it's definitely worth trying again.
Thanks, fascinating result. I admit the first thing that popped in my head was also, wait, but experiments have shown that water makes it stickier. But then that last bullet point in your conclusions was that it's been falsified. Can you just clarify, like, how were those falsified, or like why were those experiments wrong? I'm just really curious.
Yeah, so from my understanding, so they are basically the same group of people. So if you look at the author list, they are more or less the same people. And from what I heard from them, so it seems like in the earlier experiment, they have some problem preserving their sample at low temperature. So their sample probably melt a little bit. So in that case, their measurement, so in the early days, so before 2019, may be misleading.
Okay, if there's a question online, so yeah.
Hi, so question online from Octavio Aguilera. Very interesting talk. People usually use the fragmentation velocity of 1 meter per second for silicate dust based on experimental results. Why do you find a larger fragmentation velocity? I missed that bit in your conclusions.
So what we did is we first tried to measure the maximum grain size, so just based on SED fitting. And also for the viscous disk, we can try to measure, so what is the turbulent velocity, and then measure what should be the average collisional velocity between dust particle. And with a lot of assumptions, so it came to the number, so the fragmentation velocity should be in that range, and we only got the lower limit. So there are some of the assumptions in the calculation.
Okay, we can still take one more quick question. So yeah.
I don't know if this is necessarily quick, but I'm just curious, is there enough mass to form Earth in situ there? And if not, and if the grains need to drift inwards anyways, can they not grow to larger sizes as they drift inwards and then lose the ice once they cross the snow line, but preserve, I mean, they're going to lose some amount of size, but preserve some of that growth?
Yeah, thanks very much for this question. So allow me to use my backup slide. So yeah, so in FU Ori, so there's only a lot of dust mass according to our SED fitting, and we also found that so in most of the class, so the dust mass is probably of the order of 100 Earth mass within the inner few 10, well, like 20 or 30 AU region. So we have an estimate 200 to 400 survey, well, 200 to 400 gigahertz survey for 47 class. So this in the Taurus or Riga region, and you can see this is the SED. So we contribute a variable model with a single power law with a spectral index. So for most of the sources concentrated to 2.0 plus minus 0.2. So this indicates that most of the class of disk in the Taurus or Riga region, the optical depth at 200 to 400 gigahertz band is at least 5. So the lower limit is 5. And the lower limit of the dust mass in the inner 20 to 30 AU region is probably around 100 Earth mass.
Okay, thanks again for Baobab. So the next speaker is Adrian Hosch. I hope my pronunciation